That was the uniform one talking about. What was it they gave you? The uniform curve from
1 to 3.
And the one you were worried about asked you to find what?
It was letter I and K, but I don't remember the exact.
Oh, okay. It's number, which one was it?
74.
Here we go. Okay, so I says, what's the probability x is, well, 12 is less than x, so x is greater than 12. Given that x is less than 28. The original picture, I really want this to make amazing amounts of sense. What happened in normal probabilities back in chapter 3? What happened with the given? What was the immediate thing that was different if the problem said given something?
The denominator?
The denominator changed. Yes? Because given, we're talking about dogs. I can throw out all the cats, so the bottom is going to change. Right? The total number of things I've got decreases. Right? So I really want you guys to realize how this is exactly the same. What did the picture look like here? It looked like 1 to 53, and the height would be what? 1 over 52. So what did the problem give me from the beginning? It could happen anywhere from 1 to 53. That's what we're given to begin with. What are we given now?
48.
It's got to be less than 28. So that picture no longer correctly describes the situation. What is it going to be now from 1 to
28.
28? So how tall is it going to be now?
28. 128.
No.
127.
127, because that's 27 across.
Okay.
What's beautiful about that is, for a uniform curve, isn't it length times height? Do you guys agree with me that the height kind of normally gives me the denominator? Right? Yes? Maybe? No? You guys hear me? What's happening? So normally on these problems, before that problem, all the bottoms are going to be 52 because it's going to be some length, some width times 1 over 52. So 52 is going to be the denominator. This is a given. The denominator changes. So now I can just draw this greater than 12, find that area, and I'm done. You could use the formula, but as normal, the formula makes it worse. Because there's a visualization I give you. I don't have to use a formula. Do you guys know? Maybe? That's how you do a given with a uniform curve. You just chop parts of the curve off, and then the height's got to change. I really hope you guys understand. Do you guys see how that's the same as before? Denominator changes because the height gives us the denominator. So the denominator changes just like it did before. Kick ass. What was it, K? Let's see, I got one good eyeball. Hold on. So if the other one gets all. All right, here we go. Find the minimum for the upper quarter. All right, so now we're going back to normal. It's no given. We're back to this, and we're back to shitty markers. Okay. From 1 to 53 we're back to, and it wants to know the upper quarter. So where's that going to be? Where's the upper quarter going to be?
75%.
Yeah, sure. So that means there's 75% of it here, right?
Yeah.
So how do I find that position? How far across is it to go all the way? How far is that to go all the way? From the beginning to the end, how far is that?
100%.
I like it.
Weeks.
How far is it looking at where I start, where I end?
52.
52. So if I go 100% of the way, I go 52. I only want to go 75% of the way from 1 75% of what? Yes. The whole length is 52. Yes? If I want to get to the 75th percentile, how much data do I want to pass? 75% of it. So don't I want to take 75% of 52? That's how far I want to go. And of course, it's from 1 up. So it's the reverse. It's kind of like asking you, what would this have to be so that this question is 75%? I really want this to make sense. So I know the height. I just got to figure out the length to make the area 75%. So I gave you 2 ways to look at it, and the math is the same for both ways. And maybe, I don't know. Nobody's asking me any follow-up questions. Some of you are going to sleep, so I'm going to let that one stay there. Okay. All right. Anything else from homework before we keep going? Man, you guys, I tell you, I think I beat up all my math courses about the same. But you guys look like it more than the other guys. I'm really sorry. I'm really sorry. But too bad. I'm going to keep going.
Why does it seem like the homework is kind of different from the work that like you do?
Yeah, ask me. It will be.
I've noticed that the homework is like way different from what we're kind of, not like fully different, but slightly different.
Of course it is. All right, so why is that going to be true no matter what course you're in? Why do you think? You're like, I don't know, man. Well, all right, so you're supposed to learn ideas. So we discuss the ideas in class, we do some examples. If you only ever do the same examples over and over, you'll never really fully flesh out what the idea is, right? So I totally understand that sounds like a teacher answer, and I'm sorry, I'm a teacher, so I'm going to give you a teacher answer, but that's the way it is. So, and plus, I don't always agree with the way that a book I use lays things out. So there's always going to be a little bit of tension between the way I kind of do things and the way the book kind of lays it out, but the idea doesn't change. So please, dear God, that's why I want you to ask questions if it's not clear what they want from you, if it looks like, I don't think we ever did anything like this, Jeff. That's what I'm taking questions for, yeah? Yeah.
Just real quick, for K, do we find 75% of 52?
Yes.
So
that's the
it's
first
not
step.
53. It's just, it's 75% of 52. That would be.
Because what's the whole way is 52, and I only want to go 75% of the way. 75% of the way. 75% of 52.
Okay.
Yeah. You got to be careful though, because it starts at 1. Okay. Anything else? Here's the way I like to look at it. Anybody play basketball? Did I already say this before? If you can you imagine if you're practicing for basketball? Oh God, Jeff. All right, I don't care. If you're practicing for basketball, using a slightly bigger ball that still fits through the hoop, if you could start making shots with a slightly bigger ball, don't you think you'd be even better with a regulation size basketball, right? So yes, sometimes the homework will push you. It's like the slightly bigger basketball, right? It's just the way homework kind of operates. So I try to pick homework problems that sort of are, some are pretty straightforward, bare bones, right? And then some push you. Weird shit happens. Yes. So if you're having trouble like some of the later problems in the homework, you're doing pretty well. There's going to be some kind of slightly freakier problems in there. Okay, if there's nothing else from homework, then what I want to do is review what we've learned from chapter 7 and then do some problems using those concepts. Oh my goodness, sorry about that. So what we learned in chapter 7, chicken lettuce tomato, also known as central limit theorem. It says several things. It says the larger the sample you take, the more normal the means will become. Okay, that's one thing. So that one sheet of paper had the blue and the yellow on it. We started off uniform. We took samples of size 2, and it was already pretty normal looking. If I took samples of 3, 4, 5, 6, 7, it would continue getting even more and more normal. So kind of like coming off of that, if I take samples greater than 30, then the means will be approximately normally distributed. Or what I call normal enough. Normal enough to do what? What is it? What is the immediate great thing if we know a distribution is normal? What's the immediate great thing?
We can use this chart.
We can use the chart of all the answers. I like it. Right? Chart with all the answers on it. When can I use that magic freaking chart with all the answers on it? If it's normal. So in chapter 6, they had to tell us it was normal because how many did we keep taking in chapter 6? It was always take one randomly selected person, one randomly selected goat, one randomly selected shoe, whatever the shit, right? So I had to know it was normal because there's no way that sample size is big enough. But now, it could look like any weird shit. As long as I took a sample more than 30, the means become normal. And we know this. The mean of all the means is the same as the mean was before. That's the thing where I said, if I took each person's age and averaged them up, it's the same as if I took averages of 2 people at a time. You don't suddenly all get older just because I take 2 people at a time or something. Okay, maybe. That's what that says. And then, of course, what happens to this dude? Standard deviation of the sample means gets smaller because everything kind of rushes to the middle. And it gets smaller exactly. There's my, what is that, 18? 18 puberty? It gets that smaller, exactly that much smaller. And I totally understand this is freaky ass shit. I gave you a concrete example, the one with the colors on it, the numbers in a hat. It still is freaky as shit. Yes?
That's standard deviation divided by square root of that?
Yes.
Okay.
And these are both subscripts. Yes? This doesn't say sigma divided by x. This is sigma sub x bar. The little subscript, sort of like the slope, y2 minus y1 over x. Do you remember those? The little subscripts just meant the second point and the first point. This means the mean of the sample means. Standard deviation of the sample means. Okay, I like it. All right. So this is what came out of the discussions about the little island and the alternate universe Florida and all the weird stuff. Okay, I like it. So today we're finally going to do some actual, real, concrete examples that is going to be exactly what you're going to have to do in the homework and stuff. Just in case you forgot what college you are at. So let's take a look here. Holy crap. All right, do 1A. 1A, just so you really understand, is a chapter 6 problem. Does anyone remember the trigger to know when to do this, change the standard deviation? There are two things that had to happen. Looking at the formula, I have to take a sample, yes? A sample, so I have to take a sample, and there should be a question about the sample mean. Okay, let me say this again. How do I know when to change the standard deviation? If I take a sample, because that's what n is. N is how big a sample. So I got to take a sample, and since that describes what the means are doing, the question has to be about the sample mean. So look at the first one. What's the question about? Did I take a sample in 1A? Did I take a sample in 1A?
No.
No! What's the question about? How many people?
One.
A woman, some woman, right? So that's not a sample. I'm not asking about a sample mean. That's a chapter 6 normal problem. I draw the picture, get the z-score. Okay, so do 1A. Do it. If you're not sure, draw a duck and wait. We'll do it together here in a minute. Or even better, call me over. So let's see if we can catch up to you guys. So make a z-score out of 3. What do you guys get for that?
Point.
3.2 sounds about right. 0.32. All right. That makes sense. It's positive. It makes sense because it's above the mean. So if I look up 0.32, what do you guys get when you look up 0.32?
0.6255.
Yeah, 0.32. 0.6255. I like it. Is that the answer?
No.
Hell no. Because anytime you look up on the z-score chart, you immediately, for yourself, because you were nice to yourself, you drew the damn picture. So the minute you look up a z-score, you put it below the thing you just looked up. So now you know you're not done. How do I get the actual answer?
Subtract 0.6255
Yeah.
from 1.
So 0.3745. So just a little over 37% of women have bone densities above 3 grams per square centimeter. Freakadelic. I like it. So, what happens in part B? What do I have to do first in part B?
Change the mean.
The mean won't change.
Change the standard deviation.
Yeah, so the mean stays the same, we know that. But, and I can't stress this enough. I'm not going to say something yet until somebody makes a certain mistake. But maybe nobody's going to make this mistake. What is this dude all about? What is that? What is that guy?
Standard deviation.
Standard deviation of what?
The bone density around.
Sure. Standard deviation of bone densities for who? For individual women. That is the standard deviation for individuals. It's kind of how spread out each woman is on this normal curve. Is everybody with me? I like it. Part B is asking something about the sample mean of 22 women. That does not have a place in a picture of individual women. I need the picture of groups of 22 women. I want to know every group of 22 women, how are they distributed? So I can't use the spread for individuals. I have to change it to be the spread for groups. I really want this adjustment we do to make sense. Okay. So since I've got a group, you're asking about the sample mean of that group. First thing I've got to do is change this guy, because that's for individuals. It has nothing to do with part B now. Divided by square root of what?
22.
22, that's my n. I lock it. All right, what do you guys get?
0.066.
Sounds about right. And the beautiful thing is, I really have no idea how you guys feel about this. That's the only new thing. So now I'm going to do all the exact same work, because it's the same question fundamentally, right? It's just talking about the sample mean now. So it's basically, honestly, it's going to be skinnier, but I don't care. You don't have to make it skinnier. 2.9, here's my 3. I want the area above it. I've got to change 3 into a z-score. So it's still 3 minus 2.9, but now I'm going to divide by the correct spread.
But it's not normal, so we can't use the graph.
All right, I love it. Thank you. So why are you saying that, Maddie?
Because it's less than 30.
I love it. What was it to begin with?
It was normal.
It's already normal. And the larger the sample you take, the more normal it gets.
So it's still fine to be normal.
Exactly.
Okay.
So when do I really need that 30 number to save my ass? To be greater than 30 is if I have no idea what the original is.
Okay.
Does that make sense? I'm glad you said that. That's partially why I made that 22. And then I forgot that's why I made it 22, so I'm glad you asked the question. Does everybody get that? So n's not, but yeah, because what was n in part A? N was freaking 1. Shit. Okay, maybe. What do you guys get for the z-score here? I think it's 1.51.
Or if you round up, it's 1.52.
1.52? Okay. All right, and then you do the same stuff, right? You look it up, you get the area underneath. She hasn't told me yet. Somebody else? What's the area under 1.52.
Point 9357.
9357? So what everybody else got? 9357? Where's everybody else like? Sounds good, Jeff. You got that? Okay, thank you. So then what's the actual answer? Yeah. Is that cool? You guys got that? Okay, so let's talk about this for a second. Is that officially unusual?
No.
No, it's not quite officially, but wouldn't you say if something had a 6.43% chance of happening, and it happened, wouldn't that still be sort of like, huh, right?
Yeah.
So, if I found a group, so if I went to an area of the country, and I took a sample of 22 women, and it turns out their average bone density is more than 3. The probability of that happening is not unusual, but it's really pretty low, right? So then I might think to myself, is there something about this area? Is there something about what they're growing? Is there something in the water, something in the air, something in the way they do things? Do they walk more? Do they drink more milk? Are their cows irradiated, right? Are they monster beefy cows and the milk is like raw, strong, right? Maybe, do you guys understand what I'm saying? This is the first level probability kind of statistical analysis you would do to see if there's something further to look into. Sort of like with the way they analyze, what's it called? Clusters of cancer occurrences. So the probability that some group of people will have a certain level of cancer is so much. So if you find it to be way unusual, you might think, okay, let me go in there. Is it the water? Is it the air? What is it? Right? Is there a factory nearby that's pumping out its stuff into the oceans? Do the fish have 3 eyes? I don't know, stuff like that. Okay. So that's kind of leading towards chapter 9. Chapter 9 is where we're going to start to really be able to understand a decent chunk of like a journal article doing statistical analysis. You will be able to look at it and kind of, you might not understand, depending on what it is. You know, if they're analyzing blood cells and they're using words you don't know, but you'll be able to understand the statistical meaning behind what they're saying. This is significant because P is less than 0.05. We're going to know what the hell that shit means. All this stuff, right? And chapter 8 kind of leads into it too. But, okay. So don't say anything. Think about, read through number 2 and think about part A. One little thing I'm going to correct on here next time I do this. So what do you guys think about part A? Yeah, n is greater than 30, and there's another thing too. You have to kind of look ahead for this. But the fact that we're asking about the sample mean. So we took a sample that's bigger than 30, and we're asking about the sample mean. Therefore, we know it's normal enough. So therefore, we can use the z-score chart for probabilities about sample means. Since I took samples of a sample of size 37, all samples of size 37 will become normal enough. So my sample I pick is going to live on that picture. Maybe. Now let me ask it. I think I asked this before. the sample I pick, the exact sample of 37 infants, do their ages have to be normally distributed?
No.
Hell no. Or life expectancies, I should say. No, they don't. Hell no. 37 just random things. They can be whatever the shit they want to. So so you're all like, what the hell, Jeff? N's greater than 30. I thought you said that was normal. If I plot all the freaking samples, every possible sample of size 37, that is what makes a normal curve, right? Maybe. And my sample is just one of those on the picture, so I can calculate probabilities of where it might fall. Yes?
Well, like, if we think about it with the central limit theorem, whatever it's called, you're taking the groups of samples, making their mean data points, and then plotting those, and then you just use it the same way that you would a normal curve.
Yes.
It's still a normal curve.
Yes. So the problem in number 1, this picture we drew is individuals. So of course the standard deviation works. Here, this picture we drew is groups and their means, the means of groups. Therefore, the spread number that we used in part A won't work. Now number 2, so what's different on number 2 is I didn't say it was normal, but what saved our ass was this. So if I would have said 17, we would have been screwed. We could not have done this problem at all. Okay, try to do part B. There's no, the mean is 80.2, period.
Not the mean, the standard deviation.
Oh, the new standard deviation, 3 places at least. Yeah. So of course right in the middle goes 80.2. That's the average of all the averages. Curious about less than 75. And what do I have to do right here? What should I have done first? Silly Jeff. I'll do it over here. So I need the new standard deviation, the one that works for groups. So I've got to take the old one, divided by square root of my sample size, 37. Sounds about right. 2.45, 0.
Oh, it was 2.449.
449.
5. So.
Oh, 5? Okay, so 2.5, 2.45 is fine. That's a giant decimal place. Got it. All right. So now we know what to put down here. I've got to use the correct spread. So z-score formula never changes. My data point minus the middle divided by the correct spread. And the correct spread here is 2.45. Negative 2 point something.
That's what I got.
Okay. Of course, remember, I'm trying to do it in my head, so.
It's okay, just do better next time.
I will. Trust me. I'm my own worst critic. And the beautiful thing about this problem is the question what's less than, and that's what the chart tells us. So if you look that up in the chart, you're going to be done with this problem. So if we look at negative 2.12. Get 0.0170. Now, of course, back in 2004, things were getting nothing but better. And then 2006, 2007 hit, recession. So life expectancy kind of stalled out a little bit. And then, of course, recently, we got hit pretty hard with the pandemic and all that stuff. So life expectancy dropped. But it's still pretty high up there. Of course, still less than for guys than girls, but that's just the way it is in nature. And then go ahead and finish this out. Do part C. Do part C. Part D is going to be interesting. We can at least do part C. See if this kid lives to be decently old age.
Sweet.
Change those to z-scores. .17.
You don't need to figure out if the z-score changed.
Say again, sorry?
You don't need to find out if the you used 2.45 from the previous score.
Yes. Because this whole problem is about sample of 37.
Okay.
I'm still asking, look at the question, it's all about the sample mean, right? So I've got to use that new standard deviation. So what'd you say, 1.14?
Yeah.
Okay. And this one I haven't even thought about.
0.33.
Oh, you're not even going to let me try. What is it again?
0.33.
3.3?
Yeah.
Neat. And of course, what do you do in this situation? When you have between two things? Between two firms?
Subtract.
Subtract the
Area.
areas. Good. So you never subtract z-scores because that's going to change where you are. So if you look up the areas for each one, the 1.14 one goes too far down. I want it to stop, so I'm going to chop off everything below 81. It makes beautiful physical sense. So if you look up 1.14, what do you get? 8729. So it's got 87.29% below it. That's way too much. I want it to stop here. So what's below here? If I look up 0.33, $6,293, right? So that's here. So now I can figure out what's between there. 0.8729 minus 0.6293. So 0.2436. Is that right? Sounds nice.
Right.
Huh?
What are you looking for?
I don't know. That's subtraction.
Yeah, that's right.
Okay. So, about 24% of infants born in 2004 had a life expectancy between 81 and 83 years old. That's what that is. What can you do with that information? I don't know. Whatever you want to. You could use this kind of modeling to figure out, for example, future Medicare payments, right? Budgets for the future, and they've already done it, so that's why you keep hearing about when Social Security is going to run out of money, yes? Or do you guys even care about that yet? No? Okay, I understand. I still remember getting like stuff in the mail about retirement when I was 20-something. I'm like, what the hell is this? And now I'm like,
I'm
oh.
fully prepared to just never retire.
I understand. I understand. Work right into your brain.
I think that's where it's going at this point.
Understood. She's still alive. Make her do this. What about, now this one's really interesting. What the shit does this mean? What does this mean, you guys think? What would that look like?
That looks like the two z-scores to the right from and to the left of the mean.
Okay. So the middle 95%.
Yes.
My picture's not to scale, but we'll be all okay. All right, so there's the middle 95%. And they want me to figure out the freaking ages. Well, I have to first, what's the very first thing? What connects, where am I at right now? I know the area. From the area, I could figure out the
Z-scores.
Z-scores. And from the Z-scores, I could figure out the ages, right? With that backwards X formula. This, just to let you know right now, this is basically chapter 8. But of course, there's more to it, but this is the main idea behind chapter 8. So how the hell does the chart understand that area? What's the only areas that the chart understands? Does the chart understand 95% between two things?
No.
It's not built to understand that. And I love it when the students like, chart's piece of paper, Jeff, doesn't understand anything, but you know what I mean. What can we use the chart for? We can't use the chart for that area. But does everybody agree with me? I want to figure out what this z-score is and what that z-score is, right? With me?
Yeah.
Is there to figure out this z-score, to use the chart, I would have to know this area. And of course, can anyone tell me, you guys, that area is pretty easy to get? Yes, maybe? Does anyone know what that area there is?
What do you mean?
This is 95% in here, correct?
Yeah.
How much is outside?
2.5%.
On each side, right? So there's 5% outside, so there's 2.5% on this side. That is 2.5% below that line I drew, correct? I really want you guys, we've done something sort of like this before. This is 2.5%. That is the area below this z-score. Can we figure out what that z-score is now?
Yeah.
Yeah. Yeah. Somewhere. What do you look up and where? What is 0.025? Is it a z-score?
No.
No, it's an area. So where do I find areas in the chart? In the middle, right?
Are you doing 0.025 because the other side is also 0.025?
It almost doesn't matter what the other side is. All that matters is that is 2.5% there, yes, for sure.
How'd you know that was 2.5?
And that kind of leads to your question a little bit. All right, this picture is symmetric, yes? Because it's normal, so it's symmetric, right? Okay, so everything's cut in half through the mean. So if there's 95% in here, there's 5% outside. So how much is on either side? Chop half of that. Because it's evenly, it's symmetric. Look at Woody. Okay. So, I desperately want you guys to realize it does not matter. That 95% number just got me to where I could figure out the area below the z I wanted. That's what the chart understands. Areas below a z-score. That's what the chart understands. So if I look up 0.025, what's the closest I can get? And of course I'm looking on the negative side. I can get really damn close. In fact, I can get exactly that. Has anyone found it yet? Do you guys see the 0.025? What is it? Yeah, negative 1.96. Do you guys see that? There it is, right there. Okay, I like it. So really, think about it this way. If I start at the mean, that's 50 on both sides. So the question really is, how many steps down and up do I have to take until I've got 2.5% left outside? So at the mean, it's 50-50, yes? So if I start going like this, how far do I have to go until there's just 2.5% out here? Well, I've got to go almost 2 steps. Right, 1.96 steps down. And of course, since it's symmetric, isn't the other z-score going to be 1.96 up?
Don't we know on like rules though that it's 2 steps?
Beautiful. Empirical rule. Said within 1 step was 68%, within 2 steps it's 95%, right? So why is it 1.96 in reality? Because that rule was rounded to make it easier to remember.
Okay.
So that's why it's not exactly 2. It's actually 1.96, but it's rounded. Okay. I like it. So this is negative 1.96, and because of symmetry, this is positive 1.96. So if I had asked instead, the bounding the middle 90%, wouldn't the work have been basically the same? So if it was the middle 90, there's 10 outside, there's 5%, I would have looked at 0.05, negative that, positive that, bam, bam, bam. Maybe? So you can make a whole little procedure out of it. And maybe make a chapter in the book all about that procedure. Okay.
Whatever, Jeff. Teacher shit.
I know. So how do I make these into ages now? These are z-scores. Yeah? Sorry? Yeah, so we got this bad little formula here. We just have to use him a couple times. So I really want to go, let me capture everything we want to do. I want to start at the mean, and I want to go up and down. Is that cool? 1.96 steps. Oh, Jeff, you're crazy, man. Look at you doing. You're crazy.
Wait. Why do you do the plus minus?
Because don't I want to have a z-score that's positive 1.96?
Okay.
And another one that's negative 1.96. Don't I need to change? Okay, so let me not do.
Wouldn't that just cancel out?
No, because I'm not doing both at once.
Okay.
It's just like the quadratic formula. You guys remember? Oh, Jeff, really endear yourself to your students. It's not bad enough you're doing weird ass stats. Let's bring quadratic formula back up. You guys remember quadratic formula? Wasn't it negative e plus or minus? Remember that? Square root of b squared minus 4ac, blah, 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 blah. Plus or minus just meant you get two answers. You have to do them one at a time. Right? Okay. So I can do 80.2 minus 1.96 times this, and I can do 80.2 plus 1.96 times this. Oh, you know, I thought I had my calculator here. There you go. So I would do this first. 29.204. So I want to do 80.2 minus that and 80.2 plus that. So I go from 51 basically, 50.996 up to 109.4. So 95% of all babies born in 2004 will live to between about 51 and 109 years old. What's the standard deviation? Oh, did I go too far up?
5?
I did go too far up. Good job, Jeff. 2.45, thank you. We'll do that all over again. I did it for individual babies. Good job, Jeff. We want sample means, so I do have to use the correct spread. Thank you. So if I do 1.96 times 2.45, there we go. 4.8. So I can do 80.2 minus 4.802. 80.2 plus 4.802. So yeah, if you do this, you'll get your 4.802. And then you want to do 80.2 plus that, 80.2 minus that. And so you actually get 75.4 basically up to 85. That's better. So groups of kids. So that's kind of nice that I made that wonderful mistake. The first interval was for individual babies. And this interval is for samples of size 37 to have an average age. So that's between 75 and 85 basically. Because some individual could live to be really old, but then another individual could live to be really young, and so that would average out to be in that range there. Okay, maybe. All right, that one was definitely weird. I want to do, let's see. I want to look at one problem real quick on the practice test, just to help you out a little bit. Number 4. I can't remember, I think there's a problem like this in the homework. I love this problem, and I would. That's just because it's needed. But it's a uniform probability, yes? So the first 3 questions are simple. This question's pretty simple. You just got to know the formulas, right? That's the one that's divided by 12. That's kind of freaky. Remember that? And then this one is what happens on part E. So it's definitely a uniform curve, right? We're going to find the mean and the standard deviation in part D. What's going to happen in part E? What do I need to do for part E and why? Yes. You do that thing. You find a new standard deviation. Because it's a group of 43. What's the distribution going to look like for part E? What's the distribution going to be like for part E? Normal enough because it's greater than 30. Right? This is a lot like that problem I gave you where it was normal to begin with. We took samples of size 2 and then it looked pretty normal, the histogram. Yes? Maybe? So this just goes beyond. It takes 43. It's definitely going to be freaking normal then. Okay, that's enough. That's enough, guys. So everybody's got a practice test. I'll have the answer key next time. We'll make a formula sheet next time. We'll go over whatever questions you've got. And then the test is a week from today. We'll have the quizzes graded next time. forget your IDs, your guy.